Yeah, hello everyone. Welcome to the Crunch seminar this week. So today we again have two speakers. So the first speaker is Professor Ramin Bostanabad from the Department of Mechanical and Aerospace Engineering in the University of California, Irvine. So today he will give us a presentation with title Artificial Intelligence for Engineering Design and Computational Mechanics. Dr. Ramin Bostanabad received his PhD in February 2019 from Northwestern University. He joined the Department of Mechanical and Aerospace Engineering at UCI in September 2019 and founded the Probabilistic Modeling and Analysis of Complex Systems Laboratory. His group develops computational framework and tools for analyzing and designing complex systems such as multiscale materials. These works focus on the interface of computational statistics, scientific machine learning, and computational mechanics. So recent applications have been on the data-driven microstructure characterization, multiscale materials modeling with deep learning and random processes, and inverse system identification with evolutionary programming, and a simulation of multiple data sources with Bayesian statistics. So let's welcome Professor Bostanabad for his talk.
Thanks a lot for the intro. Hi, everyone. Good afternoon. I hope you're seeing the right screen. As said, my name is Ramin Bostanabad. And in this presentation, I want to talk to you about some of the recent works that we've done on the use of artificial intelligence to solve some fundamental problems in computational design and computational mechanics, as well as material science. When George invited me to give this presentation, I got super excited because I find Crunch as a whole group to be at the forefront of this field. And another reason to be super excited is that I don't really have to explain the fundamentals of deep learning because, let's face it, everyone here is an expert. Now, my research is primarily on computational design and computational solid mechanics. And one of the grand challenges that our field is actively working on is trying to understand, analyze, and design multiscale materials. And essentially all advanced materials have a hierarchical structure that spans multiple length scales. In this image, from macro scale, where I have the components, all the way down to the nanoscale. Now, because of the hierarchical nature of these materials, we need to rely on appropriate methods to analyze and simulate them. One way is to do multiscale simulations. Now, there are multiple ways to do a multiscale simulation, but when we're dealing with heterogeneous materials, we generally don't know the so-called constitutive law that allows us to relate the applied deformation, that is, for example, strain or any measure you want to use to measure strain, to stress. So what we usually end up doing, we use a method, for example, computational homogenization, to relate the applied deformation to the induced stresses. Now, in the context of first order computational homogenization, let's just say you have this macro scale structure. This is your component. You discretize it and you end up getting, let's just say, 20,000 integration points or IPs. Each integration point of your material now in and of itself is an entire structure at the next finer length scale, which in my case is the mesoscale. Same thing happens between mesoscale and microscale. Now, when you are simulating your component, that is the macro structure, you're going to do it incrementally. And at each increment of the deformation, you have to solve a lot of nested PDEs. The reason that you have to solve those nested PDEs is, as shown here for the microstructure, is that you don't know the constitutive law. You know how in this case, the fibers behave. You know the constitutive law for it. You know how the matrix behaves. You also know, for example, how the interface and interface behave, but you don't know how the microstructure as a whole behaves. For that reason, we use constitutive laws, we discretize the domain, we solve the PDEs, and once we find the induced stress, we homogenize it, we pass it up to the higher scale. Homogenization is extremely powerful, however, it's very expensive. And one of the ways that we can speed it up is to develop constitutive laws. While we're developing constitutive laws, however, we have to make sure that the constitutive law is transferable. What that means here is that we want to be able to understand the effect of microstructure, because in realistic materials, microstructure, as schematically shown on the left here, can spatially vary. So your constitutive law should be microstructure aware. The second thing that you need to take into account is that for most materials, they are path dependent, especially when you go into plastic deformation. That is, if you go from an initial configuration to an end configuration, the response of the material depends on the path you take from going from the initial point to the end point. Now, there are different ways to develop a constitutive law. Traditionally, the beautiful minds of solid mechanics people would sit down, spend years, and develop the so-called phenomenological constitutive laws. For example, perhaps the most famous one for metals is J2 plasticity. The disadvantage of these methods or these phenomenological models is that they are developed primarily for homogeneous materials. And if you try to apply them to heterogeneous materials, a lot of assumptions goes into them. And as a result, people generally built in quite a lot of calibration parameters into the model to compensate for the missing physics. Now, we took a different approach. We wanted to develop data-driven constitutive laws. And obviously, we're not the first to do this. The whole idea is to generate a bunch of data and then try to learn from that data. However, this generation process and the learning process, both of them have to be congruent with the application that we have in mind. So remember, we want to learn a constitutive law that is microstructure aware and also consider plastic deformations, which are path dependent. So in the data generation pipeline, what we end up doing is that we generate a lot of microstructures. So this is where microstructure characterization and reconstruction comes into picture. For each microstructure, we design some material properties, and we also design some deformation paths. There are a lot of ways you can do it, but some of them are efficient. For example, you can use a GP. Some of them are a little bit less efficient. Either way, you would have a training data set at this point. Then you want to find the response of each point in your sample. For that, we use high fidelity simulation with finite element analysis. At this point, we have the training data ready. And because we want to learn essentially a path-dependent property, we essentially end up using sequence learners. For example, RNNs, LSTMs, or GRUs. In our application, we ended up using GRUs just because they are more robust to overfitting. Now, to show the application of this framework, I'm going to walk you through two examples. The first one is actually a little bit simpler. What I have here is a fixed microstructure, so I'm not changing the microstructure at all. But what I am changing is the deformation path that I'm applying to this microstructure. So the matrix that is actually not shown here is aluminum, and it has an isotropic hardening behavior. It's very important to remember this is isotropic. I'm going to come back to it in a few slides. And the inclusion that I have here is essentially rubber, and it is bean shaped. So what we did here, following what I introduced in the previous slide, is that we took this microstructure, we deformed it using 15,000 different deformation paths. All of them are generated with a GP. One of the deformation paths is shown here. At that point, we had a training data set, and then we used it to train a deep neural network, in particular a GRU with 2 hidden layers. That would essentially allow us to replace expensive finite element simulations. A single finite element simulation here in this case would essentially take somewhere between 10 minutes to 30 minutes, depending on how many CPUs we have available. But once we train the deep neural networks, the predictions are going to be almost instantaneous. Now, to essentially validate this approach, here's what we did. We took the microstructure, we generated a random deformation path, again, using a GP. And then we compared the prediction of our method with finite element analysis. And the first row essentially here shows the comparison. As you can see, we can match the results of FEA pretty well. In the second thing, what we did is that we generated a unit directional loading path. And this was really interesting because all of the deformation paths that we generated in training were based off of GPs. And GPs by nature generate fluctuating loading paths. So this unit directional path has never been seen directly, at least, by the network. However, you can see that the predictions in terms of the homogenized stress and also the plastic energy match pretty well between our DNN and also FEA. Now, the interesting point here again is that you can clearly see that the model is learning the Poisson effect. That is, when you stretch something, it's going to shrink in the other direction, and you can also expect some stresses to be developed in the other directions. This essentially indicates that the model is learning part of the physics without us hard coding the physics into it. That brings up the question, how much of the physics is it learning? And to answer that, we looked at a very interesting and a really important topic in solid mechanics, and that is the evolution of the yield surface. This essentially shows you where plastic deformations start and how the microstructure is evolving as you load it and unload it. As we're showing here, our network is actually able to learn the evolution of the yield surface without us hard coding anything into it. Another interesting thing to note here is that, remember, the matrix that I had isotropic hardening, which means that the yield surface is going to isotropically expand or shrink. However, as you see here, because my fiber had been shaped, the yield surface is actually moving around, and it's also no longer isotropically evolving. And all of these are essentially learned by the model without us hard coding anything into it. Now, the natural next step for us was to take this approach and then try to also change the microstructure. So our focus at that point was on 2D fiber composite. So we started changing the volume fraction of the fibers, the spatial distribution of the fibers, the size of the fibers, and so on and so forth. The idea is that we want to have a deep neural network that takes in the microstructure and also takes in the deformation path. One of them is again shown here, and then is able to predict the corresponding homogenized stresses as a sequence. As shown here, we go through the same validation process as before, but here for an unseen microstructure, either with a complex deformation path or with a unidirectional deformation path. We see that the DNN results match pretty well with the FEA. A big advantage here is that once we train the model, the predictions are almost instantaneous as opposed to FEA. Now, what we're doing now is essentially expanding this work in two primary directions. The first one is, instead of learning the homogenized response of the material, we're trying to actually learn the entire field. The advantage of this approach is that, unlike the previous one where we had no idea how the homogenized response is going to look like, here we know the local constitutive laws, right? So I can perhaps use that in trainings, and this is where things connect with PIN, right? So I know the governing dynamics locally. So that's the advantage. So perhaps I don't even need to use finite element analysis to get training data. Maybe I can just use automatic differentiation to train my network. The disadvantage, however, is that this is a very complex problem, and we're not able at this point to get the accuracy we need to use that DNN in a multi-scale scenario, because even if you get errors in the order of 1e-5 or 1e-6, once you run a multi-scale simulation, the errors are going to propagate, and then the simulation as a whole is just going to diverge. I'm going to come back to this point in a little bit in the context of fluid dynamics. The second thing we're working on right now is a reduced order model, purely mechanics based, so nothing based on deep learning at this point. And the reason, there are two primary reasons as to why we're doing this. The first one is that there's no way, if we need training data to train our networks in 3D, either we're using fields or not, there's just no way we can use traditional finite element analysis to get the training data. They're super expensive. A 2D simulation in the previous case takes somewhere between 10 to 30 minutes. In 3D case, it's going to take hours. So there's no way we can generate big data using conventional approaches. So that's the first reason. The second one is, as I said before, we may end up needing some training data if we want to train a deep neural network that learns the stress field. Now, obviously, I won't have the time to go into the details of our approach here, but we're going to have a presentation in the upcoming US NCCM conference, and I would highly recommend you to take a look at our presentation there. But the goal of our approach, essentially, the essential idea is that what we're going to do is that once we mesh in a structure, we're going to have millions or billions of degrees of freedom. Our idea is to essentially cluster those degrees of freedom so we can reduce the computational complexity and then solve the problem. We can do this either at the macro scale or the micro scale or both scales if we want to do a multi-scale simulation. Now, we have a lot of cases. Here's just one of them for the micro scale. So what I have here is an RVE, which has quite a lot of pores in it. I'm going to take this RV and then deform it following a pretty complex deformation path as indicated up here. and then I'm going to simulate it with DNS. That simulation takes an hour. Then what I'm going to do is that I'm going to deform the same microstructure with the same deformation path with our approach. And doing so, I'm going to increase the number of clusters that I use in our approach. So as we increase the number of clusters, essentially, we also increase the degrees of freedom of our approach. It increases the cost as well, but the cost, as I'm going to show in the next slide, are drastically smaller than DNS costs. As you see here, once we start increasing the number of clusters from 35 all the way to 14, 18, the results we get from our approach, that is the stresses we get, match pretty well with the DNS result. What's important to note here is that a single DNS simulation here takes almost 1 hour. However, depending on the number of clusters we choose for our approach, the cost can be somewhere between 10 to 100 times smaller than the cost of DNS. This is extremely important for us because by choosing the number of clusters, we essentially have a model that has variable fidelity level. Later in the talk, actually towards the end, I'm going to introduce a really novel approach that allows us to do multi-fidelity modeling regardless of how many data sources we have. So if you're familiar with multi-fidelity modeling, for example, with the works of Kennedy and O'Hagan, usually they work with 2 data sources at a time. They can't work with, let's just say, 5 or 10 data sources simultaneously. Our approach essentially addresses that and has much more benefits. And I'll come back to that towards the end of the talk. Now, as I said, we can use the approach in a multi-scale setting as well. Here, I'm going to briefly talk about 2 particular scenarios. The first one is a macrostructure where microstructures spatially don't change. So I have the same microstructure everywhere in the structure. I'm going to simulate this structure with the conventional homogenization-based approach, and I'm going to consider that to be DNS because it's super accurate. And I'm also going to simulate the structure with the proposed method. The second simulation we do is for a heterogeneous microstructure. Essentially, I'm going to allow the microstructures to spatially vary. For this case, however, we're not able to run even computational homogenization just because the required RAM is just so much. So we couldn't actually run it. Now, the first one, as we're showing here, the results we get from DNS match pretty well with the results we get from our proposed approach. Essentially, we are deforming the structure, so we are imposing some sort of displacement, and we are interested in the reaction force, the force we need to get to that displacement. As you see here, the predictions of DNS match pretty well with the proposed approach. The difference here is that DNS, a multi-scale simulation, essentially took us almost 10 days to just do one simulation, while the proposed approach with a decent number of clusters or reduction of the degrees of freedom takes almost like a day. Now, for the second scenario, we're going to change the microstructures spatially. 2 of the microstructures are shown here. And as you see, compared to the previous approach, you're going to need a little bit more reaction force to get to the desired displacement. This is because the heterogeneity of the microstructures is going to produce stress concentration. That means the stress as a whole is going to increase, and hence you're going to have a little bit higher reaction force. Now, after this detour, let's go back and talk about the stress field, the fact that we want to learn the stress field. The reason we want to learn the stress field is because the constitutive law that we want to develop has to be able to be to account for the deformations that you see at different places of a microstructure. And this transferability is very important in material science and solid mechanics because more often than not, we have some sort of data. We want to take that data and then transfer the knowledge we have to other parts of the material. What this essentially means for us is that the constitutive law that we develop, even though we're learning the field, it has to be able to do that for any type of boundary condition we apply to it, and also for a wide range of microstructures. This essentially means that we want to learn operators in high dimensions. And to get to learning to operators, we actually started working in fluid dynamics problems, and in particular solving the Navier-Stokes equations. And one of the reasons we wanted to do that was because there is a very rich body of literature where different methods, some of them are just shown here, and I believe all of these are developed at Crunch. There's a great body of literature that has worked on similar problems, primarily in the fluid dynamics community. And we wanted to essentially build on this solid foundation, while at the same time having our overarching goal, the thing that we want to go back, we want to do a multi-scale simulation in the context of solid mechanics. Now, with all of these in mind, the approach that we propose essentially has two primary thrusts. In the first thrust, what we essentially do is that we try to learn an operator in a very small representative domain, something that we call genome. Essentially, what we do is that we look at this small domain, we apply different boundary conditions to it. Now, the boundary conditions obviously depend on the nature of the PD we want to solve. And then we want to be able to have a single network. This is as if we have the constitutive law, right? We want to have a single network that predicts the response of the material. In this case, if you're solving a Stokes equation, the flow inside the genome for a different boundary conditions. Because we're solving inside a small domain called genome, and because we were primarily interested in the Navier-Stokes equations, we call this network genomic flow network, or GFNet for short. Now, the predictions we get from a GFNet, I'll talk about the architecture and the training process in a little bit, but the predictions we get from a GFNet are actually on a very small domain. And in real applications, we want to do prediction on larger domains. This small domain is not really practical. So in the second thrust of our framework, we developed a really fast approach to spatially extrapolate the predictions of that the GFNet predicts on a genome in such a way that when you compare them side by side, you don't see actually a jump in the solution. And this is as if you're essentially building a mosaic. And because of that, we call the approach mosaic flow predictor. Now, a schematic of the approach is shown here. So if I want to do prediction on this relatively large domain, which is 4 times larger than the genome that I had, I can't directly use GFNet because I don't know the boundary, the local boundary conditions on these red lines. So what MF Predictor essentially tries to do is somehow estimate the solution in a really fast way on these red lines. And once you have the solution on those red lines, you can directly use GFNet to predict the solution in each of the subparts. Now, as you see here, one of the major limitations here is that I'm working on a square domain. And if you want to find a flow in like really complex domains, like for example, the heart picture that you have here for pin, we won't be able to do that yet. This is primarily because, again, we were interested in how solid mechanics works, the fact that we usually have cubic RVEs. Now, over the next few slides, I'm going to walk you through some of the details of how we actually fit GFNet and how MF Predictor works. One of the important things about a deep neural network is the architecture. We all know the architecture is important. Even if you have big data, having the right architecture really helps you in the optimization process. And through our studies, what we realize is that if we design the architecture based on the PDE, it actually helps us to reduce the reliance on training data, whether or not that training data comes from collocation points or from another solver, for example, AMG or FEM. In terms of, for example, LaPlace, we propose this linearity preserving fully connected because the solution you get is essentially a combination of the solutions you have on the boundaries. For more complex PDEs, such as the Navier-Stokes equations, we actually stick with the fully connected networks just because we don't really know how the solution depends on the boundary conditions. Now, as I'm going to show you in a little bit, the architecture we chose actually for LaPlace allows us to dramatically increase the accuracy while having a good reliance on the training data. Now, in terms of generating the training data, we have a couple of options. Now, for things like LaPlace, what we can do is that we can take a GP, we can generate realizations from a GP, and then wrap any of the realizations around this genome to get a boundary condition for LaPlace. Then you can solve it, right? So you can get the data by, for example, using AMG solver, get the solution inside, or you can again use this boundary condition in your training process as part of the loss and when you're using collocation points. We cannot, however, do this with Navier-Stokes equations because we can't just randomly generate boundary conditions because boundary conditions, for example, they have to satisfy conservation of mass, for example. So what we ended up doing for this is that we have some available flows and we can always run more simulations. We take our genome and we sweep available flow fields with the genome. And doing that, we end up with not only the boundary condition, but also the solution. Now, if you want to use the solution in the training process, you're all set. If you don't, you just take the boundary condition and then you use that in the training process. We also looked into quite a few other options. I'm going to walk about some of them for more details. Please see our paper, which is available on arXiv. One of the things that we realized early on was that adaptive regularization really helps us in training, not only in getting better models, but also in avoiding local optima. And what I mean by adaptive regularization, in particular for Tikhonov regularization, is that we start off with a pretty large penalty for the coefficient, usually known as gamma. And then as we're going through the training process, we reduce that. This mechanism sometimes in the mathematics community and the statistics community is known as continuation-based approach. In the computer science community, they have, I think, names that sound better. So they have methods known as teacher, students, or curriculum learning. Essentially, if you want to solve a big problem, difficult problem, you simplify it somehow, you solve it, and then you gradually start to make it more and more difficult so that you can actually solve the difficult problem. This is essentially what this adaptive regularization is doing for us. Another thing we did, and this really helped us in the case of LaPlace from Navier-Stokes, as I'll tell you in a little bit, we didn't actually use collocation points. But for LaPlace, when we use collocation points, we actually changed the location of collocation points during the training process. And that change is based off of the magnitude of the gradients. So whenever we look at the prediction of the solution by the network, we can calculate the gradient very fast using automatic differentiation. And we look and see where the gradients are large, and then we try to place more collocation points at those areas. We're also looking into different activation functions. I know, for example, at Crunch, different activation functions have been developed. So we're also working on those. A lot of ongoing research essentially on this area. The point here is that we can improve the performance of GFNet in prediction, and that in turn is going to improve the performance of our approach as a whole. Now, when it comes to MF Predictor, the idea that we have is as follows. So let's just say we want to solve a simple problem, Laplace equation in this domain omega. Well, once we solve the Laplace equation here, we would have the solution anywhere in the domain, right? So here's what I'm going to do. I'm going to divide this big domain into two parts, so omega 1 and omega 2. And at this point, I have the solution in this blue line right in the middle, right? Because I solved the PDE in the original domain. Now what I'm going to do is that I'm going to solve two boundary value problems. One is in omega 1, and the other one is in omega 2. I'm going to find U1 in omega 1 and U2 in omega 2. And then if I combine them, and if I compare them to the initial solution, I'll see that they actually match U. This is essentially what we want to do with MF Predictor, right? So the difference, however, is that in MF Predictor, I don't know this blue line, right? So what I do is that I take an initial guess, right? So it can be anything. So I put zeros or some random values. And once I have that initial guess, I'm going to solve the PDE in omega 1. I'm going to solve it in omega 2. Then I'll have U1 and U2. Obviously, U1 and U2 are not correct solutions because my initial guess was probably way off. Now, what I'm going to do now is essentially to try some sort of an averaging between U1 close to the red line here and U2 right here. And then I'm going to update the initial guess that I had on the blue line and go back, solve the PDE again. And I'm going to continue doing this process until I get a converged solution. Essentially, what we're doing here is that we're solving a boundary value problem, right? So we're trying to propagate the information from the boundaries to this blue line. And once that information is propagated, we can essentially solve the PDE in omega 1 and omega 2, and that's going to essentially allow us to have the solution in the entire domain. Now, this obviously is a little bit inefficient because we're just updating the prediction in one line and then updating it based on what happens close right to the left or right to the right. What we can do in a better way is to use something we call auxiliary genome. So it's very similar to what we did here, but we have an additional step. So once I have the initial guess, I can solve for U1 and U2, right? Using GFNet. So this prediction or solution is super fast and accurate because it's just forward use of the model. Now, once I have U1 and U2, it essentially means that I would have the solution on this vertical red dashed lines. One of them is down. here, the other one is right here. What I can do now is to use the genome that we have, or the GFNet, one more time. This time I'm going to do the prediction in this red domain. And once I do the prediction, I can update the solution on the shared boundary between the two basic genomes, essentially this blue line. And using some iterations, we can actually show that because we're using this auxiliary genome, we can dramatically speed up the rate of information propagation from the boundaries to the interior. And that essentially is shown here. So we go all the way from 300 iterations in our approach, all the way down to, I believe, almost 10 iterations. So the convergence is achieved in 10 iterations. Now, let's see how this method performs in different PDEs. So let's start with LaPlace, much easier than Navier-Stokes. What we do is that we solve the Laplace equation in this domain of size 1 by 1 for a wide range of boundary conditions. So we're going to change G based on a Gaussian process, and then we're going to solve the boundary value problem here in this domain. This is essentially very similar to how DeepNet would operate. Once we have this, we're going to use this GFNet in the context of MF Predictor, and we can do prediction on any domain that we can build without genome. Obviously, as I said before, if you have like something like a circle or an ellipse, you can't cover it with the score genomes that we have. But for many other types of simulations, for example, the logo that I have here, we can actually use our method. Now, initially, what we did was that we had very crude implementation of our approach, and we achieved an MAE of somewhere between 2.6 E-3 on this large domain. So that takes into account the error that we have from GFNet and also from MF Predictor. So two sources of essentially error. And it took us somewhere around 10,000 seconds to do the prediction. Now, once we train the network, that process is done. There's no retraining happening. So all the time you see here is just a prediction time. And the number of samples we used in LaPlace was around 8,000. Now, we've been working on it primarily on how we actually do the updates and the process we actually use to do the predictions. We have improved it a little bit. The MAE has decreased just a little bit, 2.12 E-3 compared to what we see in the literature. This is a pretty good accuracy. And the prediction time has also decreased to almost 1,400 seconds. It's important to note here is that the domain that we did the training on is of size 1 by 1, but the domain that we're doing the prediction on is 1,200 times larger than that. Now, let's talk about Navier-Stokes. This is actually why we started working on this part. So for Navier-Stokes, we started with 2D incompressible Navier-Stokes equations. We specifically started working on cavity flow. So we have a lid that's moving with a non-constant velocity. We have some training data. We got the training data from OpenFOAM. In particular, we have 2,100 training data. We didn't use collocation because we observed that the accuracies we get are a little bit better when we actually use training data. A lot more information about this is provided in our paper. And because we are changing the boundary conditions, it's important to know that we're not training our network for a particular Reynolds number. Actually, the Reynolds number is changing from 0 all the way to 500. However, we refrain from saying that if we go higher Reynolds numbers like 2,000, 3,000, we're going to learn turbulence, because turbulence is by nature 3D. So as long as we're in 2D, there's no turbulence. And we also use, as I said before, adaptive Tikhonov regularization. So the training data we had, as shown on part A of this figure, are on genomic levels, so very small flows. And then once we train our network and then we use it in MF Predictor, we can do prediction on a wide range of geometries for a wide range of boundary conditions. So I have two examples here. One of them is, again, a simple cavity of size 2 by 2 in terms of how many genomes that I have, so 4 times larger than the domain that we did the training on. The second one, which is very interesting, and I'll talk about the streamlines in this one as well, is 12 times larger. And it's essentially an L-step cavity where, again, the velocity of the lid, the horizontal velocity, is changing from the left to the right. As you see, we're doing a pretty good job in terms of prediction, even though the model has never seen directly vortices of this side. And in particular, as I show in the streamlines, there are actually 3 vortices here. One is here, the other one, this is the big one, the major one, and then one is down here. So the network has never seen such flow structures, but yet it's able to kind of like capture that structure. Now, in terms of error analysis, how do they look like? Well, When we started working on Navier-Stokes, we realized immediately that the auxiliary genomes that we use for LaPlace, the one that I talked about that we put right in the middle, were actually not enough. In particular, if we just use 9 genomes, where we only have just a few auxiliary genomes that try to propagate the information, our MF predictor was unable to appropriately propagate the information from the boundaries to the interior region. So what we ended up doing was to increase the number of auxiliary genomes that we use in the prediction. And that essentially allowed us to pretty much capture the flow in a really good way. If you go and if you use higher number of auxiliary genomes, you can't gain much in terms of accuracy, but the cost is going to be higher. Now, to kind of like benchmark this against what's out there in the literature, we took one of the models that's already available on GitHub. So this is actually from Paris, George's former student. So what they have is essentially a lit-driven simulation, but their velocity of the lit is constant. So they have a velocity of 1 on the top. We took their network, we tried to reproduce their results, and we were successful to do that. Then what we did is that we took the very same architecture, so we didn't change the architecture, and then we provided it with more collocation points and more training mechanisms, but we tried to train it on a varying lit velocity. So as you see here, the velocity of the lit is changing. However, because we fixed the architecture, we were not able to train a good pin. Now, obviously, if we change the architecture, perhaps we improve the generalization power of the network, we would be able to train a good pin, but this really shows you that to train a good pin, it's important for us to come up with a good architecture and then train it based off of that. In our approach, however,
Ramin, I have a question. Why didn't you use DeepONet here?
We can use a DeepONet here as well. So the whole idea was to just compare it to pin. For DeepONet, as I said before, for a DeepONet, that would be similar to our GFNet. So that's exactly the same. So
also there's an alphabet of pins. For example, if you use the X pin that you showed earlier, I'm sure you can do it. Or if you use the self-adaptive.
X pin in the paper as well. So X pin, what it does is that you essentially try to propagate information based on the PDE on the boundaries, right? In our approach, we actually don't do that. We just rely on the model that's already fitted. Now, when we try to, again, compare with XPin, this is what we did in the paper, is that we have to set the stage right. For example, XPin shows the power when you actually have multiple GPUs, right? So you can train on different, decompose the domain, do the...
No, not just the number of GPUs, the flexibility for multi-physics problems. Yes. I can have a different activation function close to the boundary layers than the bulk, right?
Yeah.
So
yes.
that's the...
So and another thing is that you are training your network on a smaller part, so it becomes easier for the network to learn it, becomes more accurate. For what we did in our paper was we kind of like fixed some of the parameters, right, for either XPin or pin, and then just the idea was to show that even though the architecture is fixed, you would become a little bit sensitive unless you want to do the retraining a little bit more. So again, here, either pin or variations or the alphabet of pin, I'm sure they can capture this cavity. So it would actually be quite simple to them, but you would need to change the architecture a little bit. So if I change the boundary condition for pin, it's going to be affected. For DeepONet, again, that's exactly what GFNet is trying to do.
Okay.
All right. Now, how do these streamlines look like? Well, as I said before, the GFNet that we had has never seen vortices of this type, right? So it has never seen a big vortex like this. And in particular, it has never seen a flow that has 3 vortexes. So what we started off doing, we actually saw that most of the errors that we get in terms of MAE actually comes from the large vortex. That's where you have the large velocities. And once we looked at the streamlines, we realized that, and this is what we did in what we got in the initial studies, our network is essentially unable to really capture the effect of the boundary conditions, right? So the streamlines you see at the bottom, physically speaking, they don't make sense. Now, through the process, what we're doing here essentially, we're essentially trying to build better and better networks. And one of the interesting things that we actually tried, and it actually improved the performance of our model, was that I asked my students, can we use data from flow in a pipe? So we had some simulations in flow in a pipe. I was like, okay, let's just take our genome, scan or sweep the flow in a pipe, get some more training data, and then use those in refining our model. And as expected, that actually helps. So it doesn't matter if you're trying to solve flow in a cavity or flow in a pipe. The fact that you're learning an operator, same thing that DeepNet is doing, provides you with great flexibility in terms of handling or solving different problems. Now, in the upcoming conference that George is actually chairing as well, we're going to provide you with more updated and more interesting results. Now, one of the benefits of deep learning, as we talked about in the context of solid mechanics and fluid
Ramin,
mechanics,
can I make an observation? Can we look at the if we look at the evolution, going from the third from the left to the fourth from the left, right, versus the ground truth, you're actually improving the big vortex. But if you look at the corner vortex, it's actually the third one has the right vortex, small vortex on the bottom, but not the big one. Then the next one has the big vortex, but not the small one. Actually, you are adversely affect. So the evolution is not monotonic. Let's put it that way. Yeah. So it is one of the reasons that we actually want to look at streamlines is because the MAEs, it's just a scalar, right? So the MAEs we get from all of these are actually pretty close, right? So all of them are in the order of 1 e -3. But when you actually look at the streamlines, you realize that some of the physics of the problem is not preserved. So we need to work much more on how we're actually training our operator layer, GFNet, which is again, similar to a DeepNet, and how we couple the predictions from that. And that's a correct observation. So we have how do you know, the question, the reason I'm asking is because there was I think a question on the chat that they were asking, how do you choose the right number of genomes? So I guess as small as possible, but not too small. But the question here for me is, how do you know that you're done? Because here, for example, you're not done by any means of imagination. You know, and you have a long way. You have a long way to go before you converge here.
Yes, but the thing is, it depends on how you define the convergence, right? So
convergence is very simple. The L1, never mind the L2, the L2, the L1 norm or the H1 norm, you have to converge because you want to compute stresses. So you need to have in the H1 norm, evaluate this in the H1 norm. You really need to. Do I have the same wall shear stresses? And the answer is no.
Yeah, absolutely.
I have the same vortices for mixing purposes for application. The answer is no. Even if you take an engineering quantity of interest, but the question is, how do you know that? Because this type of decomposition, and I agree, it's a great idea. I was used by my advisor Tony Patera for the parametric PODs and so on, the Lego approach to mechanics. In solids, in statics, it works. I doubt. I mean, I would say if you have just one cutout, it would work nicely. But if you have multiple genomes, it's just too much, and there's no way. I mean, what's the strategy for convergence? That's what. Otherwise, the novelty of the idea is there, of course. But we don't know. Let's say I don't know the ground truth. How do you know? Are we there yet? You've heard that before, right? If you have kids, they always ask that question.
Yeah. So the convergence we're using now is actually we're not using the ground truth nor the PDE for now. So the convergence we have is that when does the prediction of MF predictor doesn't change from one iteration to another prediction, right? So the reason you don't see this improving is because the accuracies of either MF predictor or GFNet, primarily actually GFNet, right? The convergence that we look at, the convergence criterion we have, is essentially how much the flow prediction is going to change from one iteration in our own algorithm to another iteration. Now, it will be more systematic. So there are a couple of things we're currently working on. One of them is that instead of this iterative approach, we're actually working in an optimization-based approach that's a little bit more expensive, but it's much more systematic in terms of how the objective function is decreasing. What we're also doing is, as part of that objective function in the optimization approach, we're using the physics of the problem. Because right now in the MF predictor part, when we try to match the predictions, we're not using any part of the physics. So we're not using the PDE form, in this case, Navier-Stokes equations at all. What we do is that, again, we just simply update our prediction. We can use the residual loss, or essentially what you use in training the alphabet of PIN, essentially, to figure out how good our predictions are. At this point, we haven't done it because, again, that would require us to update the mechanism of the prediction, the mosaic prediction, which is something we're working on. It's based off of optimization. But yes, I do agree that.
I mean, why here the lower vortex? The lower vortex is order 1 errors. Why it doesn't satisfy the boundary conditions?
The major reason that it doesn't satisfy the boundary condition is because of the error that you get from GFNet. So remember, what we're doing here is that even for a GFNet, let's just say a depot net, think of it this way, a depot net that you have fixed the square, the domain, and then you keep changing the boundary conditions, and you want your depot net to be able to predict the flow, whatever the boundary condition, right? Now, we use training data, training data from OpenFOAM to train our model, and we didn't hard code the satisfaction of the boundary conditions. So even if you just use a depot net or a GFNet by itself, you would have some error on the boundary conditions. That's just from the neural network itself. It doesn't have anything to do with the iterative process. Now, what we're doing now is to actually use what is called distance functions. So some people have used distance functions in the literature.
Yeah, we had a talk. We had a guy who gave a talk in Crunch Seminar before. Yeah.
Yeah. So that's an interesting approach that we can combine with our GFNet, which would be essentially a flavor of DeepNet plus that distance functions, which is going to allow us to hard code that boundary condition, and that's going to resolve these issues that you see. Because here, these essentially have to be parallel with the domain. However, they're not. And that's, again, something that we're constantly working on. Does that answer your question, George?
Yes, sure. Thank you.
Okay. Now, what we did in solid, and I'm going to be a little quick here for the third part of the talk. So what we did in solid and fluid mechanics here was that we didn't hard code anything into the neural network. We just developed the right learning algorithm. And that's essentially thanks to the latent space. So neural networks take the data in latent space, and then once they're in the latent space, they can learn the structure of the data in a much better way. We want to do the same thing, but we want to solve material science problem where we truly have data, small data, and we also don't know the underlying governing dynamics. In particular, we want to optimize, let's just say, a material composition whose general stoichiometry is M2AX. Now, for each of these positions, I can pick a few elements from the Mendeleev table, and this is obviously a combinatorial problem. The way we can find the material composition that has the largest bulk modules here, for example, is first you can go in the lab and build the microstructure, or you can do very expensive DFT simulations. The question we're asking is that, do I really have to do 240 simulations to get to the most optimum, or can I get there with fewer samples? Well, to do that, we're going to be using Bayesian optimization. The way it works is that you get some initial data, you fit a probabilistic model, and then you use it in an acquisition function that determines you what's the next best experimental simulation that you have to do. Now, to use Bayesian optimization in this case, we need a probabilistic model, which is going to be GP. But GPs cannot handle categorical data, which was the case in our case. So we have different elements. They're not quantitative. Now, I'm going to skip this. I'm sure all of you are familiar with GPs. They have many advantages and some disadvantages. The one disadvantage that we want to address is that they cannot handle categorical or qualitative inputs. And to do that, we introduce latent map Gaussian processes that not only address that issues, but we can also use them for multi-fidelity modeling, and we can also use them for calibration in a really flexible setting. The whole idea of latent map Gaussian processes is that it allows you to work on mixed data sets. So the example I have here, I have two quantitative variables, x1 and x2. I have the conventional app with y, but I have two inputs, t1 and t2, which I cannot really measure the distance for them, and hence I cannot use them in GP. So what do we do? Well, in LMGP, we start by converting each combination of the categorical variables into a quantitative prior representation. There are many ways to do this. One simple way is to essentially use a grouped one-hot encoded version of the inputs that we have. At this point, we have a prior quantitative representation, which is obviously and probably far from the truth. So what we do here as the next step, we take a parametric transport map that allows us to go from the prior representation into a posterior representation. One simple way is to use a matrix whose components are essentially some sort of variables that we have to solve for. Now, the number of columns of the matrix is something that the user can choose, and it's essentially provides you with the dimensionality of the latent space. Once you have this, you can plug it in any conventional correlation function, and you can actually solve the problem you want with any optimization package. The beauty of it is that you don't really have to change anything, and it's also very effective. At that point, we have a latent space, which actually has a very nice structure. To demonstrate that, I'm going to look very quickly at this complex borehole model that's usually used in the meta-modeling literature. Everything is quantitative here. I'm going to take some of the quantitative variables, convert them into categorical variable, but LMGP is not going to know anything about the underlying value. It's just going to see 1, 2, 3. Those are essentially categorical variables. It could have been A, B, C, or D. Now, we trained the model using some training data, and we looked at the latent space. We see that the structure clearly shows two principal directions. Now, if we reformulate the underlying function, we see that it actually depends on the categorical variables in two ways, L over KW and TL. By inspection, we can see that the latent space is actually encoding these two numbers in a really nice way. Now, going back to the problem of material optimization, we actually used LNGP directly on the training data set with 40 initial data. And we also use GP, but GP requires domain knowledge, someone to sit down and featureize each of the categorical inputs. We compare the performance. LMGP not only performs better, or in Bayesian optimization, it converges a little bit faster, but it also doesn't require you to convert manually data from a quantitative nature to a qualitative nature, and vice versa. Now, LMGP can be directly used for data assimilation and data fusion or multi-fidelity modeling. The idea is that we want to fuse the data together, right? It's extremely simple with LMGP. All you need to do is to put an additional categorical variable that determines the sources of the data. If you have 10 different sources of data, it's okay. If you have 2, it's okay. You don't actually have to specify which one is high fidelity, which one is low fidelity. The model is going to learn the relation between the data. Here's one simple example. Again, high dimensional. What we're doing is that from top to bottom, we're increasing the level of discrepancy in the data. We have very few data points from the high fidelity and more data from the low fidelity. All of them have noise. Once we fit the LMGP, we can clearly see in the latent space that as you're increasing the discrepancy level, the distance between the data sources, in particular from the high fidelity, increases. In terms of accuracy, we're doing much better than the competing approaches, for example, where you can fit joint GPs together. With a little change in the kernel function, we can also use LMGP for calibration. All you got to do is to just add in one more parameter or as many parameters as you want to estimate. We can show this with very simple example here, where I only have 5 high fidelity data and I have 2 different low fidelity data sets. If I want to use Kennedy-O'Hagan's approach, I get to pick essentially one of these models. So YH with YL1 or YH with YL2. Either way, just because there's just too much imbalance between the high fidelity data and low fidelity data, Kennedy-O'Hagan's approach is unable to learn effectively. However, LMGP achieves not only better performance, but also shows you in the latent space that the second model is not as good as the first one. Now, I'm over time.
Ramin, I have a question here. Because I can see how you manufacture the functions, and if I plot one versus the other, it's basically a linear correlation. The question is, can you handle nonlinear correlations? Can you have multi-values?
Yes, and that's something we're actually submitting the paper to JMD. One of the things we're working on is potential functions, which are highly nonlinear. And we actually show, I'm not sure if I have it, but if you give me a second, I think I can dig up the slides. But as we show, compared to Kennedy-O'Hagan, which consider a linear additive function, we're not doing any of those assumptions. So we can actually imagine the example actually we have, I think, is the inverse of this, right? So 1 over this function you see here. And we actually show that our approach not only provides you with better accuracy, but can also, again, in the latent space.
But I'm not asking only linear. You know what I mean? Non-linear, not just non-linear as opposed to just a straight line. I mean multi-values.
Yeah. So so if you see here, again, this is like sort of dependence. I don't know if you're familiar with the potential functions we use in stress analysis. One of them, for example, is the Arruda-Boyce. It's highly nonlinear, so it's really, you really had to define principal stresses and then calculate some values based off of that. So we are working on that, and same thing here. So it's a simple example, but we observed the exact same thing with really complex examples. So I can send you the, I don't think I have it in the slides, but in an email, I can send you the exact function and the results that we have.
Okay.
All right, so I'm way over time. I'm going to skip this summary. I'm going to thank you all for your attention. Special shout out to students and postdocs and the collaborators. And again, thank you all. And I would like to open the floor for questions.
Thank you very much, Professor Bostanabad, for your great presentation. So I see a question in the chat.
Yeah, perhaps I can.
Yeah, how to choose the right number of genomes for the MF predictor?
Yes, so that's a great question. So for LaPlace, if I go all the way up, so for LaPlace, what we did is that we essentially used one overlap, as shown here. So anytime you have genomes, we essentially use some sort of an overlap. If you go to, in 2D, you'd essentially have multiple auxiliary genomes overlapping with each other. Anywhere we have a shared boundary between the basic genomes, we would essentially put an auxiliary genome. Now, as I said, in the case of Navier-Stokes, that didn't work, so we added one more layer of genomes. So that's what we tried. And if we start increasing the number of genomes, again, the convergence criteria we have is based off of just the prediction. When does the prediction from one iteration to the next prediction doesn't change? That's our convergence. We're not looking at the PDE itself. Based on that, if you start using a lot of genomes, all you can gain, if it's excessive, is that the computational time is going to increase. So the accuracy is not going to change. It's just that the computational time is going to increase.
Yeah, thank you for your answer. Is there any other questions?
May I ask a question?
Yeah, sure.
I have a few comments over the LED-driven cavity case. You mentioned that since it is a two-dimensional case, there is no turbulence. Two-dimensional does not imply that there is no turbulence. In some of the, it is true that it is a 3D phenomena, but when you solve for the when you're looking at the temporal average case, and if one of the direction is homogeneous, so you have those values to 0, but to 0, and what happens here is that if you're looking at the temporally average fields, the correct equation to actually look into is the Reynolds average Navier-Stokes equations, and in those equations, what you will find is, as a result of turbulence, you will have 6 to 9 unclosed terms. There are 9, but the 3 of them are symmetric. So it boils down to 6 terms. So a large body of academic and otherwise research actually looks into how do you build those turbulence models. So two-dimensional does not actually imply that, and a large body of it actually looks into those two-dimensional phenomena because it is.
Pavan, I think Ramin was talking about classical turbulence with the 5/3 law. You still have turbulence, two-dimensional turbulence, but the cascade is different. So I don't think he meant that actually. But for the cavity flow, he's a solid person, so we forgive him. For the cavity problem, basically the turbulent flow there will be above about even unsteady. For the square cavity, you have to go to Reynolds number about 5 to 8,000 to make it unsteady, never mind turbulence and so on. But it's a very stable flow, actually. But do you have anything, never mind about the fluids, Pavan, do you have any questions about the genome network?
I just wanted to point it out because the LED-driven cavity is a very classical case. So I just wanted to point it out, where are the bodies buried, that's it.
Yeah. Thank you. Yeah, so we started, when I started working on this, we have like an expert in our department. You probably know him, Saeed Al-Gabashi. The first thing he said to me was that turbulence is 3D by nature. So I took that as a fact, just because it's Saeed. And we sort of used it when we were working on this particular cavity problem.
Yeah, him basically made, the interest, of course, to have stretching of vorticity, which you don't have that because you don't have the U grad omega term in the it's directly zero. But I have a question on how do you know? How do you know that the genome flow net converges? In other words, do you sleep well at night? You think that everything is converging and you're happy, or because you have enough? Yeah, there's no theory. That's what I mean.
Yes.
In DeepNet we have a theorem, and we kind of, at least on the approximation side, we sleep well at night. There are other issues, but how do you know that it converges the genome?
So that's a great question. So again, similar to what you see in, so if I go right here, similar to what you see in DeepNet, right? So in theory, in approximation theory, you know that, okay, it's going to converge if you provide it with enough flexibility, if you have enough data. But in reality, that's not really the case. So it really becomes a choice for us. What's the best accuracy we can get, and is that acceptable or not? For example,
Ramin, I don't mean that actually. I mean that you don't really know if this network is a universal approximator of operators. You don't know. I don't think there is a theorem that says GRU or a single neural network is a universal approximator of operator. You use something which approximates functions to approximate operators, but that's a leap of faith.
Yes. So the whole idea for us was that if that approximation is accurate enough, and I'll go back to that accurate word, then we can essentially assemble these predictions together and then do, again, extrapolation in space, having in mind how we want to use this in the context of solid mechanics, right? So remember, in the solid mechanics, what we want to have is essentially a constitutive law, right? Which achieves an accuracy on the order of 1e minus 9 or 1e minus 10. So what we get right now is about, on the genome scale, is 1e minus 5, right? And our approach was primarily based on the MAE that we see when we're training the network. So we didn't actually look into the approximation theorems and how accurately we're learning the PDE. What is the error, where is the error coming from? We were primarily interested in the MAE we get, for example, on the maximum errors we get. Again, primarily because we had this idea that at the end of the day, we want to go back and we want to develop a constitutive law for solid mechanics and then use it in multiscale simulations. Again, one thing we can do is, as I said before, GFNet is exactly the same as DeepNet, right? Essentially what we're doing.
No, it's not exactly the same. I disagree with that. That's why I asked you the question. DeepNet is based on very solid theory, the theorem of universal approximation of operators. Yes. So we have the branch, and specifically we have the trunk, which you don't have the trunk. So you don't have a continuous output space. So GFNet is half of DeepNet.
Yes. So
the GFNet is half of DeepNet. It's not the same thing, because what you have there, we we separate out input and output. And I think Lulu is online who developed also. Lulu, do you see any similarity between GFNet, not the objective, but in terms of construction of the architecture? GFNet, does it look to you like a DeepNet?
Yes,
not
actually,
the objective.
Yes, for the network showing here, for the linear case, actually the same as DeepNet, as the linear case of DeepNet. But for non-linear case, they use the standard fully connected network. I would say if we have enough trained data set, maybe it works, even for fully connected network.
But the trunk space is not, the output space is not continuous, right?
It is.
You don't have two neural networks. You only have one neural network for everything.
So what does that have to do with the continuity of the output space? So
because
you want output space, or essentially X, you want to be able to do prediction. Let's just say go here. You want to essentially be able to do prediction anywhere in this domain, right? Is that what you mean by the continuity?
No, if you look at the theorem, you have to look at the theorem, the approximation theorem. You will see what I mean about that.
So, okay, so maybe I can mention two things. In terms of the objective of what we're saying here for GFNet and DeepNet, as you said, objective is the same. So we're changing the boundary condition. We want to be able to predict the solution, right? The architecture, however, is different. At some point, so I can perhaps get in touch with the postdoc that was working on it. At some point, I believe he did try the architectures that you propose in DeepNet, and we also have tried a wide range of architectures, CNN based or fully connected based. And at the end of the day, what we ended up choosing was just based on the accuracy, like MAE that we got from the training. And the reason we make that decision was because we want to be able to couple these predictions. So the lower the MAE we got in the training process, the better it was for us to couple them together. Now, perhaps we can perhaps do the training in a different way, so one might outperform the other one. But in the studies we did, we observed that such a training or such structures that we're showing here, in terms of, again, just the MAE we get from the training, it performed a little bit better than the other architectures. Again, we're not doing the math here. We're just.
I don't think so. I don't think so. I don't think you actually push hard enough, because we have done this. Actually, if you look at our Nature paper, and beyond other papers, we do have comparisons with FNNs for the same problem, the same users. Okay. We have a comparison with sequence to sequence with CNN. And yes, the accuracy may vary, but the main thing is the generalization error. Which architecture generalizes well? So that is really the issue. The issue is all these architectures, you can train them in a certain way, and you can get very small training error. That's not the issue. The issue is actually the generalization error, and that's the expressivity. That has to do with the expressivity of the network. The Fourier network from Caltech is very expressive, is limited to simple domains, simple boundary conditions, smooth solutions, but it's very expressive, although there's no theory. So that is here. I'm sure this is expressive. It's just there's no theory to guarantee that two things. That actually there are two main things when you deal with operator regression. One is make sure that you have universal approximation properties for the operator, not for the solution. So that's why it doesn't matter what you find in one solution, because you're talking about solutions, not operators. And the second one, and that's important, I think, the Caltech, the FNO may not have that, how you break the curse of dimensionality in the input. In other words, as I go from epsilon in approximation to epsilon over 2, how much more training data do I need? Do I need twice as many or 4 times as many, or I need exponential as many? Because that's the curse of dimensionality. The 120 pages paper of Mishra from ETH show that DeepNet actually breaks the curse of dimensionality. And that's very important. People have not paid attention to it, but he brought this up as an issue. And his latest paper as of this week also shows that pins themselves are also breaking the curse of dimensionality. And that's important because we all want to scale up our problems, right? To bigger inputs, big real estates and so on. And so these are issues that otherwise people are, before you have tried to do different neural networks, different architectures, for a specific application, it works like a charm. But to generalize like you're doing, which I think is you have a great idea, use this as a building block, like we did in DeepMNM, for example. DeepMNM, we use DeepNet as a building block. But DeepNet itself, we guarantee that is a universal approximation. So when Lulu built this, was basically following the math. And of course, you can change the branch to a CNN or a GRU, or you can do that. But having the trunk and the branch working in tandem, in parallel like that, and crossing the fields, that gives you something that comes directly from the theory. For example, the theorem of Chen and Chen, when it applies to functionals, not operators, but functionals, is just a standard summation. It's a single network. So in fact, your GRU will be ideal. We published a paper on approximating functionals, and we had an LSTM, and that worked like a charm.
Yeah.
But that was like something as a function of time, like an ODE, not a PD, for example, where you have this multi-dimensional space. So but like a functional, right? So if I want, for example, the pressure as a function of time, integrated over part of the domain, that's a functional, right? So so that part you can approximate with a single neural network, and that's theoretically justified. So I'm not disputing all the results that you show us are actually accurate. I'm just raising an issue that is overlooked because, you know, in engineering, whenever you work something, don't break it and make it bigger and better. But underlying of that is the theory, which sometimes could be a very practical tool, namely to tell you that, look, there's a case of dimensionality here. You cannot lift it. So you cannot really scale it. Or I know you're trying to use Genome for small domain and so on, but you may have lots of wiggles, multiple scales already in the genome. How do you transfer that to the bigger domains, and does it have the capacity? And in the overall framework, I think the question that it was in the chat about the number of genomes is an important question if you sort of try to go beyond empiricism to build some sort of you know, how big is big, and of course that depends on the problem. That it's hard to find, but the issue is maybe you can have one of your postdocs or collaborators to look at the expressivity and the approximation ability of the GNF that you
yeah, great points. So one of the things we tried, and perhaps we can improve on that, was that I think the architectures you're proposing in DeepNet paper, they are already available, right? So we took that architecture, and then, as I said, we did the training. Perhaps we just didn't run it enough or something. So the optimization error, if you will, because the error you get from a deep learning network comes from different sources, right? So it has reconstruction error, optimization error, and so on and so forth. One of the error sources was perhaps larger than what we had before. So I can put my students and postdoc maybe in touch with Lulu here, and then they can figure out perhaps something that we did wrong. And that would be ideal for us as well, because we can improve the performance of GFNet, and that's just going to improve the framework as a whole.
Yeah. Well, with Lulu and Xuhui and Sanjay, three postdocs, we're working now on a fair comparison between operator regression networks. So we'll be happy to do a comparison ourselves for your network.
Yeah, that'd be great. Thanks. Yeah, so we can share the data. We have no problem with that. Share the architecture. Anything should be fine. Any other questions?
So I have one question. So for the network here, basically you are using the standard fully connected network, right? In the previous slide.
I believe you're referring to this one?
Yes.
Okay, yep. Standard fully connected.
Yes, I think the reason it works because in each small domain, G is the boundary on the small domain, and in the small domain, G does not really change dramatically. So essentially, the dimension or the intrinsic dimension of G actually is small because it's small domain. That's why if you have a data set, if it's larger than the standard fully connected network works in practice, I think that could be the reason why the standard fully connected works, because in your small domain, so G actually is simple on the small boundary. And as I also mentioned, so for the left, the linearized case, so this linear case is the same as the linear DeepNet. Actually, this is the same. So this is for the linear case, actually the equivalent to the linear version of the DeepNet. If we took the branch net to be linear network, then this actually is equivalent. And also, actually, I'm not more interested on the convergence on the second stage. So when you do domain decomposition, then you're iteratively updating the boundary. So do we see in practice whether it always converge or it may diverge?
So in our case, we've only seen convergence, but the convergence might be to some wrong solution, right? Again, the convergence in our case is defined as how does the prediction from in one stage changes from another stage, right? So we always see that convergence, which is nice, but the converged solution might not be a good one, as shown here. So for Navier-Stokes, when we were not using enough genomes to help propagate the information from the boundaries to the interior, what we ended up doing was we added more genomes. So that just helped us with more mechanisms to essentially propagate information. The exact way of where we place these genomes and how we do it, we're explaining it all the way in the paper.
Yes, okay, thank you. Actually, I have read of this paper a few weeks after its own archive. Yeah, it's nice.
Good. Hope you liked it.
Yeah, because recently I'm doing a similar thing on domain decomposition, basically, but it's slightly different setup. So that's why I'm curious about the convergence, because sometimes using network as a surrogate model, because the network model, the network solver is not accurate. Then if it's not trained well, then the convergence would be a trouble.
Yeah, so that does happen in some cases where you end up not only not converging, but just diverging to some value. So if you start, if you just keep doing the iterations, the numbers are just going to grow. Fortunately, we've never observed that. The only thing we've observed is that we would converge to a wrong solution. That's primarily because the network we train, I mean, we make sure that the data we put in, it's pre-processed a little bit. Same thing with the outputs. That is taking into account the dynamic similarity and things like that. We scale the inputs like velocity, pressure, so they are in a reasonable range between say 0 to 1 or -1 to 1. That really helps with that avoiding the divergence issue that you talked about.
I can give you a very simple example of divergence. Okay. Now, no matter how you do it, neural networks or finite elements, or if I take a domain like this, which is 10, and I take a domain which is 3, okay, and I pass Dirichlet, and I pass and I do the sparse iteration, and I pass Neumann data from the big domain to the small domain, and Dirichlet data from the small domain to the big domain without overlap, that diverges. Okay, that's a 200 years old Schwarz algorithm, and there's a theorem that shows that in order for this to converge, the ratio of the big domain to the small domain, the master domain to the slave domain, the size has to be larger than 1. Okay, so now if you overlap the domains like you do for Genome, that of course is forgiving. Or if you do like relaxation techniques and so on, there's a way. So to diverge is very easy based only on geometric information, okay, on sizes. If you pass Dirichlet data like you did, there's no theorem that guarantees. If you look at the Schwarz algorithm, the Dirichlet boundary conditions does not guarantee that you will ever converge. If you do what Schwarz proposed, which is the Neumann-Dirichlet, it guarantees that you will converge in a finite number of iterations. That's a theory again, so you have to be. All these things is careful now how you put it together, because we don't want our methods to depend on the students or our postdocs, and they may or may not have a good day. So,
yeah, that's always the case. Yeah, fortunately, we haven't run into any issues. Again, perhaps that's overlapping really helps with that. But there are more ways we can look into it, or perhaps we can design examples somehow that trick our algorithm to diverge. We're going to look into that as well. Any other question?
Yeah. If there is no other question, let's thank Professor Bostanabad for his great presentation. Yeah, thank you again for giving this talk to us.
Sure. Thank you for the invitation and the great comments. We're going to keep in touch, and then we'll see how we can progress. Thank you all.
Yeah, sure. Thank you very much. So
thanks, George.
So now let's welcome our second speaker, who is Dr. Xuhui Meng from our Crunch group. So he will present give a talk with the title Learning Functional Priors and Posteriors from Data and Physics, which is about his recent work. So let's welcome Xuhui to give this talk.
So can you see my slide? Can you see my screen?
We can see your slides.
Okay. Yeah. Thanks, Henry, for your introduction. And today I'm going to talk about learning functional priors and posteriors from data and physics. And this is a joint work with Liu Yang. His outline. First, I'll introduce the motivation, and then I'll introduce how to learn functional priors from data and physics using generative adversarial neural networks or GANs. And then I will show you some results on both the forward and the inverse PD problems combined with pins, and also some results on combined with the DeepLab. So to quantify uncertainty in PDEs, we have two methods. The first one is Gaussian process regression, and the second way is Bayesian physics-informed neural networks. So let's take this as an example. L is some operator U is the solution for a PDE, and F is a forcing term. And in the first method, we can first use Gaussian process as a surrogate model for the solution. And then if the operator is a linear one, and F is also a Gaussian process. And if we have some data on U and F, we can then get the posterior of both U and F. But in the Gaussian process regression, we may need some more advanced techniques to extend it to nonlinear programs and also big data programs. And in the second method, we use instead of a Gaussian process, we use Bayesian neural networks as the surrogate model for the solution. And in the Bayesian neural networks, each weight and bias is a distribution instead of a point estimate, as in a fully collected neural network. And in a similar way with similar with pins, we use the automatic. We can use the automatic differentiation to encode the PDE. And if we have some data on the right-hand side F and also some data on U or boundary condition, we can then estimate the posterior for the hyperparameters in a neural network based on a Bayes rule. Like this is the P theta is the prior for all the weight and bias in a Bayesian neural network, and this term is the likelihood, and this is the posterior. And this method can handle nonlinear PDEs and also big data programs, but as you can see, because each weight and bias is a distribution, so if we have a neural network in the parameter space, we'll go to very high dimensional. And the second problem for this method is if we want to specify prior in a functional space, it's not very clear how we can tune a distribution of the weight and bias to fit the specified functional prior in the functional space. So recently, Liu Yang proposed to use the generative adversarial neural networks to learn stochastic process. So this is the schematic of the generative adversarial neural networks or GANs. So in the GANs, we have a generator and also a discriminator. And the generator takes in the input noise, which is generally a Gaussian distribution, and also the coordinates acts as the input and outputs a function. And the discriminator will take in a generative sample and a true sample, and it can tell the difference between the generative function and the true function from the training data. So after training, this is the version of GAN we used in our work at WGAN, and this is a loss function for the generator, and this is a loss function for the discriminator. So after training GAN, we have a surrogate model to map from the input noise cassette to the to a function distribution or a stochastic process. And similarly, we can also use the automatic differentiation to. We can also apply the automatic differentiation for the output of the generator to encode the PDE, which will give us the physically informed neural GANs or PI GANs. In the paper, they demonstrate that the GANs can learn both Gaussian and non-Gaussian processes. So inspired by this work, we are trying to use the GAN to learn a function distribution as our prior in the Bayesian framework. So this is the overall process of our method. So we first train a GAN using historical data. Here, historical data can be both a specified function distribution, say a Gaussian distribution, or it can also be the simulation data and experiment data in the past. So, and we can use this the historical we call all the data as a historical data here, and we can use this data to train the GAN to map the input noise to the functional space. And then if we get some new data for here, we use U and F to denote the functional prior. If we get some new data for U and F, we can then, based on the Bayes rule, we can get the posterior of the, or we can get the posterior samples of in the latent space of GAN, and then with the generator, we can map the input the posterior samples in latent space of GAN to the functional space. In this way, we can get the posterior for both U and F. And as for the posterior estimation, we can use Hamiltonian Monte Carlo and also normalizing flows. So here's a brief comparison with the Bayesian neural network. So in the GANs, the stochasticity is from the input noise, and in the Bayesian neural networks, the stochasticity is from the weight and bias. And because the neural network is very expressive, so the input noise is generally very low dimensional, and we can fit even with a very low dimensional input noise, we can fit a very complicated stochastic process or function distributions. But in the Bayesian neural network, in our paper, we use a 2 hidden layer with 50 neurons per layer, and it goes up to more than 2,000 dimensions. So this will lead to some difficulty in posterior estimations. But in the GANs, because the input noise is generally say up to 100 dimensions, it would be beneficial for the posterior estimation. Here are some results. So in the first case, we try to use the Gaussian process as our functional prior. So this is the functional prior. This is a Gaussian process we will use as a Gaussian with a functional prior, and we randomly draw 10,000 samples from U, from this Gaussian process, and to learn the functional prior. Input noise for the GAN is a 40-dimension Gaussian noise, and then after learning the functional prior, we assume that we have 10 noisy. We have 10 noise measurements for a new U here. This is the U here is different from what we used in learning the functional prior. So in the first case, we assume that we only have 1% noise in our new training data here, and this is the prediction from the Gaussian process. The red dashed line is the predictive mean and the failure zone and the two standard deviations. And the GPR regression will be served as our reference solution. And this is the posterior prediction from the present method. So as we can see, both the predictive mean and the predicted uncertainty are very similar as the Gaussian process here. And then we try to increase the noise level in the training data U. Here we use 10% noise in the measurements of U. And this is the prediction from Gaussian process regression, and this is the prediction from the present method. As we can see, the results from the present method are very similar as that from the Gaussian process regression. And we also test the effect of the dimensions of the input noise. So here we use the same training data as in the last case, and this is the results from the. So in the GANs, we first use 40-dimensional Gaussian noise as input, and in the second case, we reduce the dimension of the input noise from 40 to 20, and as we can see, the results for the second case is very similar as the Gaussian process regression, also the one with the 40-dimensional Gaussian noise input. This which is due to the highly expressive of the neural network. Then we can also apply this method to the meta-learning for function approximations. So in the meta-learning, we will have a task distribution, which consists of many similar tasks, and we will have some data, data from in the meta-learning. We'll have two stages. The first stage is the training data stage, and the second stage is the testing stage. So in the training data, training stage, we assume that we already know some data from this distribution. So we'll first gain some experience from the prior knowledge using the historical data. For example, the blue points here, and then if we have a new data set from a new task, and say the red point here, and we at test the training and as the testing stage, we will make use of the prior knowledge to improve the model performance. And for the regression process, we can view the task distribution as a distribution of functions. So we can use the GAN to learn a function distribution as our functional prior, and then if we get some new data for a new task, we can then get a posteriori based on the learned functional prior. So this is a 1D regression example for the math learning, and we assume that the task distribution is a family of functions as follows. Here A and omega are two variables, which belongs to two different uniform distributions. And to learn a functional prior, we can randomly draw 2,000 samples for U, and for each U we'll use 30 equidistance points to resolve U. And the input noise for the GAN is 10-dimensional Gaussian noise. So after training the GAN, we can randomly draw 1,000 random samples from this function distribution, and we can also, after training the GAN, we can also use the GAN to generate 1,000 random to generate 1,000 samples for U. As you can see, the generated U are very similar as the true samples from given function distributions. And in the meta-learning community, there is a baseline for the meta-learning method, which is model agnostic meta-learning. So we also use the same training data as we used to train a GAN to train MAL, model agnostic meta-learning. And after training MAL, this is a prediction. This is a prediction from MAL, and so as we can see, after training MAL, we only have average memory on all the tasks in this task distribution. But in the GANs, we will have memory on the details of each sample or each task in the task distribution. So if we have some new data which is from a new function and is not in the training data set, for example here, we use the U equals to sin 10x plus some noise as our new test function, and the noise in the measurements is 5%. So the blue points here are the training data for the new test function, and we only use 4 training data here. And the red dashed line is the predicted mean from the present method, and the field zones and two-standard deviations. And the method dashed dotted line is the prediction from the MAL. So as we can see, MAL can still infer the correct phase for regions we don't have any training data, but the amplitude are not very accurate because we don't have any training data here. But for the present method, we can still get a very accurate prediction for the regions even we don't have any training data, because we have learned a very informative functional prior from the training data. And for comparison, we also present the results of the Gaussian process. In Gaussian process, the prior is trained by maximize the marginal likelihood. So as we can see, for the regions we have, if we have training data on some region, the predictions can be very reasonable. But for the prediction in the regions we don't have any training data, as we can see, the predictions are not as accurate as this method, because we use a very informative functional prior in our method. And so in the second case, for the first case, we can see that we don't have any noise in the data for learning the functional prior. In the second case, we assume that we have the noise is even larger. We have very large noise in the data for learning the functional prior, and the test for the data used for testing, we assume that the data for used as in the posterior estimation is the same as in this case, and we just add some noise in data for learning a functional prior, and the test function is also the same as this one. As we can see, even have very large data state and large noise in the data for learning the functional prior, we can also get a very accurate prediction for the posterior here. And we also test a case in which the test function is out of the distribution of the learned priors. So as we can see, because the prior doesn't cover the new function here, so as we can see, the prediction are not as good as in these two cases. And also, the similar results can also be observed in the MAL. So if the test function is not in the prior distribution, it's very difficult to get a very accurate prediction. Now we go to the PDE problem. In the first case, we can see there are 4 problem, and the problem we can see that it's a nonlinear diffusion reaction system, and D is the diffusion coefficient, KR is the reaction rate, and this is the bound condition, and this is the exact solution for U, and the omega I it's a uniform distribution here, and we derive we can then derive the F based on a given solution of U, and because this is a forward program, we will learn a functional prior for F, and we use 10,000 samples for F to learn a functional prior for F, and the input noise for the PI gun is a 40-dimensional Gaussian noise, and for the posterior estimation, we assume that we only have 10 noise measurements for F, and the noise in the measurements is 5%. So with the given measurements for F, we are trying to obtain a solution for U with the uncertainties. So this is the functional prior for F, and the bullet points are the training points and noise measurements for F. And the red dashed line is a predicted mean for F, and the field zones and the predicted two-standard deviation or uncertainty for F. And this is the prediction for U. So similarly, as we can see, for F, for here, even we don't have any training data, we can still get a very accurate prediction. This is because we have a very informative prior for F, which is learned from the historical data here, and also for U here. As we can see, the computational error for U are bounded by 2 standard deviation in the whole region. And for comparison, we also present the results of the BPIN. And this is the same architecture we used in our BPIN paper. And for the prior, we use a standard Gaussian distribution for each weight and bias in the neural network. And this is the prior for F in the BPINs. And this is the predicted mean and uncertainties from BPINs. So as you can see, the predicted mean, both the predicted mean are not as accurate as our present method, and also the predicted uncertainties are much larger than the present method. This is because we have a very informative functional prior learned from the historical data. And now let's go to the inverse problem. So the equation is the same as the previous one, and the D is the diffusion coefficient, which is known, and this is the boundary condition, and we keep the solution for U fixed as the we'll keep the solution for U same as the previous case, but now KR is unknown, and which is the function of U, and we're trying to infer both. So we're trying to infer both F, KR, and U based on some based on some measurements on F and based on some measurements on F, U, and KR. Although KR, just it's the inverse problem, so we only have some measurements for F and U, and then we use 10,000 samples for F and KR to learn the functional priors for both F and KR. And in the input noise for GAN is a 60-dimensional Gaussian noise. And so in the GANs, we will have two, because we now we have two functions. So we will have two generators which share the same input to generate both F and KR. So after learning the functional priors using the GANs, we assume that we have 10 measurements for F and 2 random observations for U. Both all the measurements are noisy, and the objective is to infer U, F, and KR based on the noise measurements here. And these are two plots for the functional priors for F and KR. And this is the predictions, the predictions for F, U, and KR. As we can see, the predictions for F are very accurate, even we don't have any training points here. And so here we only use 2 points we only use 2 measurements for U, and we can get a very accurate prediction for KR here, even we don't have any training points for KR. And so in all the predictions for F, U, and KR, we can see the computational errors are bounded by 2 standard deviation in the entire domain. So in the last 2 cases, we assume that we explicitly load the PDE. So in some scenarios, we may not load the PDE. So in these cases, we can use dipole operator neural networks as a surrogate model for the PDE. For example, for this case, we only have some observations on F and U, but we don't load the equations. So we can use the dipole to learn a map from F to U. So in a dipole, we have a branchlet which takes in F, the function F as the input. And we also have a trunklet which takes in X, the coordinates as the input, and use the inner product as the output. So we use different functions of F and U, the predata F and U to train a dipole. So once the dipole is trained, we can get a map from the input from the input F to the output U. So to combine the functional prior and the dipole, we first use the prior data F and U to train the dipole. Once the dipole is trained, we will get a map from F to U. And then we can use the same data we can use the same training data for F to train the GANs. So in the GANs, the generator will take in X on the input noise and outputs F to train the GANs. So after training the GANs, we'll have a surrogate model from the which maps the input noise to the function F. And then we can combine the output of the generator to the input of the branch that. And then we'll have a surrogate model. We'll have a surrogate model for which maps the input noise to F. And then with the dipole, we can have a surrogate model which maps the input noise to F and then to U. So after training the GANs on the dipole, if we have some new data for F for U and F, we can also use the Bayesian inference or Bayes rule to get a posterior of the input noise, and then with the trained generator and dipole, we'll get a posterior for F and U. So in the first case, we can see the fractional diffusion reaction system here. D is the coefficient, it is the diffusion coefficient, and Kr is the reaction rate, which are well known. And alpha is the fractional order. So we assume that alpha is from this distribution, and F is a Gaussian is the following Gaussian distribution. And then we randomly sample 10,000 samples for alpha and F, and we can use some numerical method to solve this PDE to get pair data from pair data of F, alpha, and U to train a dipole. And we can also use the same data F and alpha to train a generator. So after train the GANs, we can get after train the GANs and dipole, we will have a map. We will have a surrogate model to map the F and alpha to U, and also the input noise to F and alpha. So in total, we'll have we can use the generator and the dipole to map the input noise to both F, alpha, and U. So after training the GANs and the dipole, we assume that we have some noise measurements on F and U. We're trying to infer F, U, and also the fractional order here. So this is the learned functional prior for alpha, and this is a prediction for F and U. As we can see, the computational errors in both F and U are bounded by 2 standard deviations. And this is the predicted alpha with a 1 standard deviation, and this is the exact alpha. So as we can see, the predicted alpha is very similar. The computational error between the predicted alpha and the exact alpha is bounded by 1 standard deviation here. In the second case, we can see the two-dimensional saturated flow in porous media. And this is the K is the conductivity and H is the pressure. And this is a boundary condition for the PDE. Here K is we consider K as a stochastic field, which is generated from a truncated Gaussian KL expansion from the following Gaussian process. So in the dipole, we map the conductivity to the pressure field. And in the GANs, we map the input noise to the conductivity field. And we use 30,000 samples for 30,000 per data K and H to train a dipole, and we use the same samples to train a GAN for K to train a generator to train a GANs. So after training the GANs and the dipole, we will have a surrogate model which maps the input noise to both K and H. And then we assume that we have some noise observations on K and H. here we use 10 random observations on K and 10 random observations on H. Both all the observations are noisy here. And we're trying to infer the K field and also the H field. So this is a computational error between the predicted K and the exact K. And this is the computational error for H. So as you can see, the computational errors are bounded by the total standard deviation for both K and H in this case. So in all the previous cases, whereas we only consider the field is space dependent. Now let's go to time and space dependent. Time and space dependent problem, which is the displacement of the marine riser. So this is here is a schematic of the marine riser, and it will vibrate because of the flow of the water. So, and this along the riser, we only have a few sensors here in the riser. For example, we have here we have 1, 2, 3, 4. Only have 4 sensors along the riser, and we would like to reconstruct the displacement for the whole riser. And so the first step in our method is to generate a training data for learning the functional priors. To generate the data, we have 4 new methods. The first way is to get the data from the lab experiment, and the second way is the simulation data. In this case, we use the reconstructed data based on the experiment, and this is some parameters for the riser. And here, this is a schematic for the displacement of the riser. So X is the inner direction of the riser, and this is a time t. So we use a sliding window to generate samples to train the guides and to learn the functional prior. And the details for the sliding window is here. So in each window, we will have 16 by 16 noiseless measurements, and then each window will cover 2.4 seconds. And the time step for the sliding window is 0.01, and the time interval for the samples to learn the functional prior is from 1 to 150 seconds. And we use this data for training, and we'll predict the displacement for this time interval. And the input noise for the guide is 20-dimensional Gaussian noise. So here we can see 2 cases. So the first case is we only have 1 sensor along the whole riser. And the second case, we have 3 sensor for the along the whole riser. So this is the prediction. So the black triangle is the new data for posterior estimation. So this is a predicted computational error for the predicted mean and the reconstructed displacement. And this is the predicted uncertainty. So as we can see, the computational error here is very large. And most of them are not bounded by 2 standard deviations here. So for the second case, we increase the measurements from 1 to 3. And this is the computational error. As we can see, the computational error are reduced significantly if we increase the sensor from 1 to 3. And most of the computational errors are bounded by the 2 standard deviation in this case. Yeah, that's all I have. So I'll stop here to take any questions.
Thank you very much for this presentation, Xuhui. So I have a question about the part where you combine the functional prior with DeepNet. Yeah, with DeepNet. So why do you need to combine with the DeepNet to learn a function of between F and U if you already have the historical data of U?
So if we have some new data on U and F, we only have We want to quantify the uncertainty in the predictions of dipole. So in original dipole, we don't have any uncertainty, right?
Yeah.
So say let's take an example. So you can use the simulation data to train a dipole, and for the test at the testing stage, if you have some noise measurements for both U and F, you want to quantify the uncertainty in the prediction of U. So you can use the Poisson method.
So this combination is more for quantifying the uncertainty, right?
Uncertainty, yes.
Okay.
And the second way is so after training a dipole for input F, the number of the location, the number of the sensors for F are fixed. But if you want to use this framework to quantify the uncertainties in U and F, you don't need to fix the location, the numbers of the sensors for F. You can only have, say, for example, here in the training. So in the training, I use say 40 equal distance points to resolve F. But at the testing stage, I only have 10 random points for F here as for the input of the dipole.
Okay. Okay, I see. There, thank you. And yeah, is there any other questions for Xuhui? Yeah, if not, then let's thank Xuhui for giving this presentation. And so this ends the Crunch seminar this week, and hope that everyone have a good weekend and see you next week.